Right. Well, welcome back, everyone. I'm really not sure what I've gotten into by agreeing to share this. So I will postpone thanking the organization. Just go ahead. The topic is status of the STRAIN program. There are panelists, and I'll at least guide the discussion on focusing on the quantum gravitational aspects of that question largely, since this is a quantum gravity workshop. And I'll just start with sort of one slide on question. If I can get my slide to go. Here we are. Okay, so what are key facets of the problem of quantum gravity? And I grew up as a physicist in roughly the 80s. That's when I was doing my PhD and so on. And if you ask anyone what the problem of quantum gravity is, in one word, in the 80s, the problem is non-renormalizability, right? Of course, the perturbative theory. So that very much has been a traditional focus, and that has guided a lot of the work on the subject. But as time has gone by, we've evolved into a position where at least some of us believe there's a more profound problem facing us, which is this problem of non-unitarity, in particular in the high energy sector, associated with quantum black holes, however you make them. So those are certainly two key facets of the problem of quantum gravity, key sort of problems that we face in trying to quantize gravity. And then there's a whole list of things we would like to understand, of course, going beyond those sort of one-word issues, the whole list of things we'd like to better understand. One is the nature of quantum observables. What is a quantum observable? How do we define those, say, in a gauge-invariant fashion in gravity? Connected with that is the question of what is our theory of observation? How do we connect, say, quantum operators that correspond to observables to things that our experimentalist friends measure or observationalist friends measure? And those are two different questions, but they're related. Of course, if we're talking about a quantum theory, it should have something like a Hilbert space. So what is the Hilbert space? What's the structure of it? How do you think of the different states in it? What are the degrees of freedom? And what is the dynamics that determines the state or selects the state? And how do we describe something like time evolution? Of course, that's connected back possibly to this whole question of observables. And then more specifically, we would like to describe quantum cosmology in a theory of quantum gravity. Of course, in today's universe, the curvature radius, say, associated with the cosmological constant is quite large. And actually, I need to correct a small but embarrassing mistake that I made yesterday. I was referring to the 10 to the minus 30. It's really 10 to the minus 60. I took a square root accidentally, square root. But that's okay because 10 to the minus 60 only amplifies by a factor of 10 to the minus 30 all of the points that I made. Reduces, but anyway, emphasizes by a factor of 10 to the 30 all of the points that I made yesterday. Of course, much earlier in the universe, the cosmological constant scale was, say, much smaller in distance units, and so we're much closer to a quantum regime that's much further from approximately flat space. And then finally, again, we are, of course, focusing on gravity, but we should not lose sight of the fact that we are physicists and our description of gravity should connect with a description of the other forces and matter in the universe that we know about, basically the standard model so far, plus probably dark matter and maybe not a lot else. And so we would like to understand, the connections, how we describe those forces within the context of our theory. Okay, so string theory. What successes has string theory had? And the one thing that really got things going was string theory does apparently give a very good answer to this problem of perturbative non-renormalizability by just basically giving us a sensible cutoff, which makes the amplitudes perturbatively finite. And so that is something that really helped kickstart the interest in string theory community-wide. Other things also helped kickstart that. But then we come to the other questions, and here things are less clear. So, for example, the problem of high energy non-unitarity. Well, string theory does not yet have a clear and compelling answer to that, I would claim. There's the idea of holography, in specifically, say, in the ADS-CFT context. But the devil is in the details in a sense. There's a real question. What is the holographic map if ADS-CFT is the answer? And we have invested a lot of effort over decades trying to answer that question, and we still have some serious questions about understanding the nature of the holographic map. So that's why I put a question mark there. The notion is that ADS-CFT may well provide a unitary answer. That's what people who sort of advocate this point of view say, but the map is a good part of the question in that case. There's the question of what are the quantum observables and how do we think about observation? String theory at least has a partial answer to that question because string theory at least perturbatively gives us a way of calculating S-matrix elements, and the S-matrix is something that in certain contexts is useful and sensible, and we can connect with experiments, so that's all good. But there's the question of how to think about actual quantum observables, say the operators on the Hilbert space or what have you, that behave as observables, how to think about observation in finite time situations and cosmologies. All of that is a little bit less clear in string theory, so that's why I put question marks there. What is the space of states? What is the dynamics determining the state? Also, we have some notions, say, perturbatively of how that works, and even some ideas non-perturbatively, but still not a complete picture, I think. Although these are questions being posed to the panelists, so the panelists may give answers to some of these. There's the question of how do we describe quantum cosmology in string theory? And again, that has been very fertile ground. There's been a lot of discussion of cosmologies built using string tools and ingredients, but what is there a convincing and compelling story? I would put a question mark there. And then finally, the connection to the description of other forces in matter, and that is something that also helped initiate a lot of the interest in string theory of compactification on Calabi-Yau manifolds, getting close to the standard model and so on. But there, it's been a real challenge as well because, finding just what we've seen, namely the standard model plus probably dark matter and nothing else that wrecks the phenomenology in a convincing way has been a real challenge in the subject over time. So that's why I put a question mark there. So these are all questions which I think we could hope the panelists will help answer, and they will possibly have their own questions as well. So that is at least the outline of where we might take things. So what we will do is have presentations from each of the panelists I guess we might as well go in alphabetical order. Please limit your comments to 5 minutes so we can have plenty of time for discussion with the rest of the participants. And so we will start with,
Yeah, 5 minutes. 5 minutes. So I also do not know what I'm doing here. That's wishing this moment I were in a galaxy far, far away. I asked the organizers why they put me here. They said that they welcome different viewpoints. Okay. The point is that I stopped paying attention to string theory many years ago. So
that's why they put you there.
yeah, that's the only thing I can do in these minutes is to explain why and what my take about string theory is. But I have to go through a little bit of history, first-hand experiences, but also the history of previous events that I learned from older people. So you may know that in the late 50s and the 60s, there was an approach that was very popular. It is the S-matrix approach. S-matrix is the subject of this conference. And the ideology was that you do not need local quantum field theory, vertices, Lagrangian diagrams, but just jump to the S-matrix. Why? Because the S-matrix is what we need. The S-matrix is non-local. Why start from something local, etc., etc. And so people try to guess the S-matrix. And I call it an ideology because the idea was that maybe their dream was that using only logic, self-consistency requirement, and analyticity, one could guess the only S-matrix that's consistent, and that has to be the universe. Okay, so I think you are getting already a hint of where. But the S-matrix supporters were wiped out in the end, the late 60s, at the beginning of the century. The standard model was started to be built, and in particular, there was asymptotic freedom. And so remember that Young Mills wrote their paper in 1954. And that paper didn't get much attention till it was used to explain data, and it became necessary, and in particular, asymptotic freedom. So I was curious. I asked people, did data come first, or the theory came first? Of course, all the people knew I was naive in asking the question. Data came first because deep inelastic scattering was showing definitely strong interactions were not strong. So people were looking for something asymptotically free. Some people played with a bunch of photons, which is infrared free. Some people played with a model that Neil recalled 2 days ago, which is 5 to the 4th with lambda negative, but of course is unsatisfactory. And then somebody computed the beta function of Young's theory in this. I had been told that it caused a storm in the community, and those people who worked on the S-matrix approach were basically in great difficulty of finding positions. And this was a matter of weeks. Okay? But data were rich, but not so rich. And after a few years, things started going back to the other state. And so beginning in the middle of the 70s, you have supersymmetry, West-Lumino, string theory. Then you have the first superstring revolution, the cancellation of anomalies and heterotic strings. Then string theory decayed a little bit. And then there was the second superstring revolution, which is 1995, which is where I can start talking first-hand experiences, because in 1995, I was in my first postdoc, which was at Harvard, the Lime Laboratory, string theory group. I don't know why I was there, I don't know when here, but I was. And I saw things happening. So I can give you some quotes of people, and very telling. So I remind you that the ideology of string theory is that it is a theory with no parameters that can explain everything. Okay. Mm-hmm. This is it. As ridiculous as it sounds, but it is the ideology. So Witten came to give some lectures in those years, I don't remember which month, and he said the following thing. Maybe one day we will be able to interpret H bar as a consequence of a symmetry principle. Probably something that is the consequence of an invariance under changes of coordinates from a higher dimension. And to give you an example, I can tell you about the paper he wrote in those days. Probably didn't get much attention, but it explains the idea very clearly. So it was a paper about the model in 6 dimensions, which was 4 plus 2, and the 2 dimensions were used as follows. You know that in 2 dimensions, the propagator of a scalar field is a logarithm in X space. So he engineered the model so that going down to 4 dimensions, that logarithm occurred in the right places to explain the logarithms, the renormalization group law. And so the idea was, you see, radiative corrections, quantum, not quantum, they are classical in disguise. And then the ADS-CFT correspondence came in 1998, which is more or less the same thing. Although the n=4 theory does not run, it is a quantum theory, but the idea, no, it's not a quantum theory because you can see it has a classical theory in an extra dimension. And okay, the classical theory was supergravity. Actually, it is string theory, but you start getting the point, which is that basically string theory is classical. Okay, in 1996, while I still was there, I'm about to conclude very briefly. In 1996, when I was there, there was a conference on philosophy and physics, philosophy of quantum field theory, Boston University. And I went there, and I was the only one from the string theory group of Harvard going there, although we had triangulations, BU, MIT, Harvard, with joint seminars. Nobody showed up. And in this conference, Weinberg was exposed, he said that opportunistically, he was endorsing string theory in a not convincing way and not very convinced. It didn't leave much impact, but there was many people like Riet and others who attacked string theory very strongly. And David Gross gave a speech to defend string theory. And I remember one quote from him that echoes Plato's philosophy. And he said, quote, garbage around us, beauty and light up there. So this is more or less the dream they are going after. And so I went back to the string theory group and I played down. I asked Vafa, who was the leader of that group, and as if I were not aware what was going on, I asked him, and I said, look, I went there and I heard many people attacking string theory. And what do you think about it? And I said, we don't have to worry. These people are old. They will die soon and we will live. Okay, so you understand the point. I think that string theories are quantum deniers.
Okay. Ivano next. Trying to get this set up.
Yeah.
Well, that's not optimal formatting, but I think it's workable this way.
What's the problem with the post?
Oh, well. Usually. Prohibited
And the
window.
full screen isolated output.
Okay.
You would have more.
Oh, there we go. Okay.
I have some too.
I'll try to take. Yeah. So let me maybe get my clock ready. All right. Hi everybody. So, in the beginning, when I saw Steven's slide, I thought, oh, there's a whole lot of question marks. But then after actually listening to what he had to say, I must say, I think it's a pretty fair assessment of the status of the theory. And of course, I'm happy to discuss, details. But another question I've been asked multiple times here is what I find compelling about it, right? And right, so yeah, you can read everything. And I think at least one reason is that I try to start from what I thought was a common ground, and another thing I learned here is that perhaps that's not true either, which is effective field theory, right? Quantum gravitational effective field theory. And it seems like if we take its rules seriously, right, the rules of quantum mechanics and all of that seriously, like without actually throwing out anything, there are considerably more constraints in the case of gravity as compared to non-gravitational field theory, which is already pretty constrained on its own. And to me, the fact that there is a way out of these constraints, there seems to be some structure which checks all the boxes as far as these consistency principles go, is worth checking out at least. So instead of maybe throwing some of these rules of the game or changing the rules of the game at some point, it seems like there's a way to get somewhere without actually changing any of the basic principles. And so I sort of divided this slide in two basic bits, so the theory part and the pheno part. So to answer maybe the big question of like what's the status of the thing. Of course, my perspective is extremely limited, right? The field is super broad, but at least my perspective is that the theory side of things is that I feel like there has been some progress in understanding, how all of these constraints from the consistency of quantum mechanics with gravity and the effective field theory come together to make this work, like sort of in a bootstrapping effort using consistency of stuff like S matrix or black hole physics. And I think there were already, of course, glimpses of such a consistent structure in the preceding decades, studying string theory proper. But one can start from the bottom up without actually assuming anything except for the basic rules, and try to bootstrap one's way to it. And in my opinion, there has been some interesting progress in the recent decade, the single decade, I would say, on this. As far as the pheno story, that's much more complicated question. Because I think one should start from what to expect even from a theory of quantum gravity. Like, of course, in general, because of this UV-IR mixing that has been mentioned multiple times, such a theory should, in principle, predict anything in the sense of the IR and the UV. But, of course, I mean, this is what the theory should do, in principle. It could be hard to do in practice. But at least one could imagine that the UV could be somehow universal, right? Independent of the messy low energy details of the vacuum state of the theory. And indeed, this seems to be the case in string theory. As far as the IR goes, I think there is no particular reason to expect that it should be simple or unique or even just a handful of options. There are many quantum theories we know of that have many different low energy sectors, and in fact the standard model effective field theory is one of those. It has many different low energy sectors. We just happen to be able to pinpoint the one that's relevant for us because we have a lot of data in that case. So yeah, in this case, my personal opinion, limited, is that the status is that progress has been much slower in the context of phenomenology. And of course, people are making efforts in recovering particle physics and cosmology, but as Stephen pointed out, it's far away. So now I just wanted to close by addressing a few of the things that are often repeated about the theory that I feel like are simple enough to address that it's worth just putting it out there. So, for example, the story about low energy suits in extra dimensions that people often say, it predicts this, predicts that. I would say that it doesn't, in the sense that, if you actually take the formulation of the theory, at least the partial formulations that we understand more or less, and you see what they actually tell us, you realize that the story about 10D and Susie and whatnot, they are the simplest sectors of the theory, not at all the generic one, and certainly not the unique ones. So there are plenty of other sectors, low energy, vacuum and so on, that have nothing to do with higher dimensions nor low energy supersymmetry at all. And in fact, some of them have no Susie even at high energy. Then, of course, other consequences of this thing is that it's not clear what the status of dark energy as a basic ingredient of cosmology is. Because you could say, but if you have Susie, then cosmology is sort of impossible because it would break Susie. But there is no such conflict here. What I would say, if I were to commit to something in this regard, is that eternal de Sitter and or weakly coupled de Sitter, I would say they are probably excluded by the theory. That's one thing I would feel comfortable saying.
What does probably excluded mean?
I have a high confidence that the theory excludes it.
Should I be confident in your confidence?
I don't know. You can be confident in the evidence.
I'm not feeling very confident.
this for the discussion.
Yeah.
Anyway, we should wrap up.
Yeah. And of course, the story, the theory hasn't, as far as we understand, has no parameters, but of course has a lot of vacua. But then again, it's not particularly surprising because any theory of gravity has multiple vacua, including the standard Paolo effective field theory. The selection comes from outside. There's no internal consistency principle that selects vacua and low energy fluctuations for you. So the question is, how is the situation evaluated there? Let's say there's a finite but huge number of such things compared to the continuous infinities of the EFT parameters. What is the comparison there? And I think the selection has to be done from external inputs, from data and stuff like that. Then I could go on, but I think I already said enough. I think I can wrap it up.
Thank you.
Next. Slides. Okay, try to distill to 5 minutes.
Okay, to look at string theory, if you have open string, include gauge theory, and closed string include gravity. Now, if one starts from an open string, one gets closed string at one loop level through the non-planar loop. If one starts from closed string, one gets non-perturbative object called diffie brane that has the property of having open string attached to the work volume. In conclusion, one cannot have a gauge theory without having gravity and vice versa. And that is what ought to yourself in nature. In D equal 10, one gets few string theories, two heterotics, type 2A, 2B, and type 1, having only one free parameter, the string length, which is square root of alpha prime h bar. Notice the connection in gravity, the Planck length is Gn, square root of Gn times h bar. So in string theory, you have Ls, you have C and H. Now, string theory has the characteristic of being a theory of everything, not only because it describes all interaction observed in nature, but especially because it can interact only with external field corresponding to one of the field of the string. In string theory, the interaction is constructed in terms of vertex operator that are in one-to-one correspondence with the string physical state. So, so either we say that string theory interacts only with state of the string, or we may also say that everything is inside the string. So we cannot interact with anything else. String theory are more or less unique in 10 dimensions, but they live in 4 dimensions. And so we need to compactify 6 of the 10 dimensions. And this can be done in many different ways. And that is the arbitrariness. We cannot use string theory to predict or to explain what you observe at accelerator energy, but this is also the same in field theory. You cannot predict in field theory that you get a standard model. You construct a theory that fits the experiment. And so why not to do the same thing in string theory? So we can only search compactification that contain the standard model, classify them, and that is not an easy task. Check if they are stable, stabilize the moduli to connect with the phenomenology, and write down the 4-dimensional Lagrangian. Now, even if you write toroidal compactification, where you can compute everything, it's not easy to write a 4-dimensional Lagrangian. Now, what about non-supersymmetric theory? There is a lot of work that maybe Ivano can discuss later on. Can we have a consistent non-supersymmetric theory in consistent string theory based on non-supersymmetric theory? And finally, string theory is an extension of field theory. It's not in contradiction with field theory, but is an extension. So you compute everything in string theory, you perform applying going to 0, and you get gauge theory and Einstein gravity. But you can do the zero-slope limit in many different ways and select practically any field theory that we want. Although string theory is an S-matrix theory, multi-loop diagram were constructed long before knowing that it was a string theory. So although you have an S-matrix which is only on shell, nevertheless, you can compute multi-loop and they are consistent. In the bosonic ring, all loops have been constructed and they can be used to derive loop diagrams in field theory. This has been done for many theories, phi cube, pi to the 4th, gauge theory up to 2 loops. The 1-loop beta function and 2-loop vacuum diagram Young Mills have been derived many years ago. In many cases, it's simpler to perform the calculation in string theory and then take the zero-slope limit rather than compute directly in string theory. So that's another use of string theory. And finally, just to say that I'm not talking about things, that's the G-loop and tachyon amplitude, where in the Schottky parametrization of the Riemann surface, so you have an integral over moduli, dVn, which is given in terms of the multipliers and the fixed point of the Schottky parametrization, and that is the integration volume. And then you get an exponential. Instead of Zi minus Jj that you get at the tree level, you get the Green's function at n loop, which can be written down in terms of the Schottky parametrization. So you can use this in the bosonic. There are only scalar amplitude, and you can compute essentially any bosonic thing. That's all I want to say.
So Neil is next, and you did not send slides. Is that
I did
correct?
not send slides.
Okay. So
So, I first of all, I haven't really prepared much to say, so one could basically say 3 things. First of all, I think Steve's summary was absolutely perfect. Totally agree with it. So I don't want really to add anything to that string theory. I did want to say, in contradiction to him, to really thank the organizers, because I think they've done something quite special with this workshop. And I think, which I see people nodding, you know, we live in a situation where younger people generally are finding it hard to see their future in academia because everything is against them. And I think the people doing quantum gravity are exceptionally courageous. You have to be to do quantum gravity. It's practically an impossible problem that we've chosen to work on. And I think this particular group of young people has decided to bring people from many different approaches together in a workshop. And that is really unusual. And so I just wanted to thank them. I think it's amazing for them to do it. It's not that surprising. These are the most courageous young people because they are working in quantum gravity. But it's great to see. And they are furthermore seeking to cross boundaries. And I absolutely think that they are role models in that respect. And I wish other young people would also seek to cross boundaries because that's how the exciting progress is going to be made. It's not by following in the wake of old people like me. It's by clashing different ideas against each other and then finding something genuine or new. So I really want to congratulate them, Alessia, Benjamin, Luca, and Straban, for bringing us all together. It's been a very, very stimulating workshop, precisely because there are all these different points of view. And the question I wanted to ask is, can we have more workshops like this, please? It's got to be organized by young people. They've got to be multicultural. And we were discussing over lunch, we need EDI in research, okay? EDI is vital for the future of the world, but we actually need diversity in our approaches to research. We need more equity between different approaches. I think the tendency of some approaches, dominant ones, to dismiss others is really destructive and discourages people from pursuing genuinely new ideas. So I think this workshop is a great model, which I'm trying to think, how do we replicate it? I wanted to add one little story to Anselmi's story, the story about string theory. You know, I was, just before that time, I think 92, I was offered a junior faculty position at Princeton. Yay, I'm going to Princeton. I'm going to apply string theory to cosmology. It's the perfect match, right? Because they know how to study quantum gravity. And I was interested in cosmology. And it took me 3 months to see this wasn't going to happen. Okay. And I went to all my great string theory colleagues and Ed Witten and David Gross and everyone. I want to use string theory to tackle cosmology. And, 500 years was quoted by a previous speaker. That may be optimistic. So, you see how much consensus, and again, the organizers have created this atmosphere where we have consensus, which is just great. So I wanted rather more short, time. I wanted to work on things that had a chance of progressing more rapidly. So I switched to observational calculations like the CMB, which have been making incredible progress. But still, the core of the fundamental theory is very strong in all of us in the workshop, for all of us in this workshop. And so the other thing I wanted to mention is that my attitude to string theory changed about 10 years ago. I was as excited about membranes and M theory and all that as everyone else, and hoped that would lead to unification. But I was in an unusual position of actually being responsible for this institute, which had very large funding and could hire almost whoever we wanted in whatever field. So suddenly this responsibility was placed on me. and I had to look objectively at which fields are actually going to be the best bets for significant progress on a finite time scale. Okay, and I came to the conclusion that it's not going to be string theory, sorry to say. At least not as conventionally approached. There are simply too many assumptions, too many, let's see, preconceptions. And whereas I think really what we need is people addressing more foundational questions, in clever ways, and above all, crossing boundaries, not just following pre-formulated lines of research. So that changed me, and I decided, well, if I've made that decision, I can't work on this anymore. And so I've got to really look on more foundational things. So the way I think of my current research is really trying to recreate something like string theory, which is far more minimal. So I think string theory is just sort of the easy route, as I would say, but with the easy route comes the extra dimensions and comes all of these complexities, which frankly I find very implausible. The reason I find them implausible is because the observations are so simple. We do not live in an apparently chaotic universe. We don't see supersymmetric particles at the LHC. Something is going on which is much simpler than string theory, but I think we can learn a huge amount from the lessons of string theory and hopefully try to create a consistent theory, mathematically consistent theory, which reflects the simplicity of the universe. So that's okay.
Okay. We will have comments. Okay.
Right.
5 minutes, please.
I want to sort of emphasize the first part of what Neil said, and we didn't clap, so maybe we should clap now for the organizers, right? And then the other things you said, I cannot understand, but we can discuss it. I don't have time, agree, but that's fine. So what I decided to do is to, at least from Twitter discussions, I kind of understood what are the most common complaints about string theory. They tend not to be about making assumptions. I don't think we make many, or about not being foundational. Most complaints that I hear is about the vacuum problem. So I want to quickly say something about that. Right, so as I said, the criticism is string theory is not delivered, lost in mathematics, not even wrong, and physics is about observations. When it comes about that last sentence, I challenge everybody working on quantum gravity to tell why it would be different from string theory when it comes to observations. It's just a basic fact of effective field theory, but I will come back to that. So if the problem is the landscape, the space of QFTs is infinitely big. So that's a way bigger landscape, okay? And of course, we fixed more than 20 numbers in the landscape by observations. And as Paolo said, what's wrong with using the same approach to string theory, which is a generalization of field theory? And somehow, for a reason I never understood, there must be some kind of a religious belief that the fundamental theory of the highest energy scale must have a unique vacuum. I think we all share this belief that the fundamental theory should be trivial. The interactions at the smallest distances, physics has always shown us the smaller you get, the simpler theories become. I've never seen examples where the IR structure of the theory becomes simpler. Okay, usually it's the other way around. QCD is a very simple Lagrangian. There's a very complicated vacuum structure. All right, so my biggest counterexample is that we already know today that the fundamental theory, whatever it will have an incredibly large landscape. Why do we know that? Because the standard model must fit in it. And as Arkani Hamid explained, once you couple the center model to gravity, there's an infinite landscape of vacuum. Okay, so you cannot say, I use the landscape argument against string theory, because already today we know that the fundamental theory of all interactions will have an incredible landscape. I think that's a proven fact. So imagine string theory does not describe the real world. Well, that's what I'm going to start with the second paragraph. So does that mean that's usually when there's a landscape, people say, oh, so this means everything goes? That's also a huge surprise to me. Working on string compactifications myself, it's the complete opposite. Whenever I try to get some effective field theory people like, it tends to not work. So once you work with string theory compactifications, you actually fall in love with how it constrains effective field theory data, right? I think this is the power. And so what we're seeing these days is that all of the possible effective field theories you can get from string theory tend to obey certain patterns. Now, there's a program called the Swampland program, which is about taking a step back, look at those patterns and ask yourself, do they make sense from a deeper point of view, from a non-stringy point of view? And what turns out to happen? Most of these patterns you can guess by Gedanken experiments with black holes or something else. To me, that is a very healthy sign of string theory. But of course, you can play this game without using string theory, and I invite everybody to think about these rules. When it comes to observations and predictive power, as I said before, if you trust effective field theory, you have to conclude that decoupling is an essential part of why physics, or actually all sciences, biology, geology, why they can progress. Okay, without decoupling, we would not have science as we have it. This also shows that the chances of observing quantum gravity, and therefore of falsifying string theory or some other, will always be extremely hard. So when Ivano said the word 500 years, I don't think he specifically meant string theory. This applies to anyone. And of course, there are caveats. As Damiano mentioned, there is the tensor to scalar ratio. This could be one of the small windows, all right? Or axion physics could be another one. But usually you're in trouble, whatever approach to quantum gravity you use. So finally, and I hope I still have a minute, perhaps. Okay, let me go quick. What I want to point to, which we don't discuss enough, is a thing that I like to call inner logical consistency. Okay, because if quantum gravity is not directly related to observations, you say this is not physics, this is religion, not true. Richard David, I think, wrote a whole book about this, okay? So, and I would just want to give an example. This is a formula you can get from effective field here. It tells you about the entropy of a black hole in terms of its area. There's a 1/4 here, and then there's a C, and this C depends on the matter content. Okay, it's a certain number, but effective field theory spits it out. A theory of quantum gravity must be able to compute these numbers. In fact, also the other ones. Okay, in some corners of string theory where we can do calculations, we computed this, we got exactly 1/4, and that's after a super long computation, and you don't know whether it will work out. More amazingly, and somehow people don't mention these results, we got the right C. Okay, so I think I challenge, and I understand now that not all approaches to quantum gravity are in a position where they compute this, but please try to appreciate how non-trivial this is. You cannot be blind to the fact that these two numbers come out of completely independent calculations, and they work out whenever we can compute them. Okay, this is not something you can be blinded about. So I want to make a controversial claim, right? I want to say I think it is completely valuable to work on quantum gravity without a single observational input, apart from the fact that we have observed quantum mechanics and we have observed gravity, because almost nothing goes in quantum gravity. It is extremely constraining to not predict something obviously inconsistent. This reasoning is part of physics, it's not part of mathematics or philosophy or religion. And that's how I would like to thank you.
Okay. Bring up the list of questions. Then, well, we could start if any of the panelists have burning questions or objections to what other panelists have said. And we'll broaden it. So,
I had one short question for you. You said you were worried about.
I'm not a panelist. I'm not a panelist. No.
Well,
It's all right.
very good. You said you were worried about non-unitarity and string theory, and it was a bit puzzling to me because the big claim about string theory is that it's always unitary. So were you talking about non-perturbative, non-unitarity?
Yeah, so I'm specifically thinking about this question of very high energy scattering, where we think we do something like form quantum black holes, and there's pretty good evidence for that. And then you can ask whether understood string effects modify the story in a way that restores unitarity and gets us out of the conundrum that Stephen Hawking left us in. And the answer is, it's not clear how string theory answers that question. Although, of course, there's a proposal of holography, but then I said what I said. I think there's a real question about how to really understand holography. So that's sort of a short version.
Yep, right.
Yes.
Maybe there's a quick thing I can add to that, which was actually partly in the slide, and I don't really have time to explain it, but there is, you don't need to actually.
Yeah, I want, I'd like to keep this up, but go ahead.
Yeah,
Go
just
ahead.
keep this up.
Okay.
So there are, at least estimates, or in some cases more precise computations of like very high energy scattering in string theory, and resummations of loops and stuff like that, which give certain signatures of what the amplitudes or cross sections would look like. And when it comes to this black hole issue of, and I think maybe you're you have in mind this classicalization that the black hole microstates start dominating the amplitudes and you get these entropy suppressions. Of course, that lies in a certain non-perturbative regime, which is hard to access. But at least these two asymptotics, if you will, these behaviors, actually do match parametrically at a scale, exactly the scale you would expect them to, the black hole threshold. Namely,
when the short
scale
field
of,
radius is the string size, roughly.
In that case, that's it. Which is in general, it's the black hole threshold, the scale of the smallest black holes available in the effective field here. So, and the same matching arises from like the degeneracy of states in the spectrum. And I think both things are non-trivial things that could have gone wrong. Of course, they are partial indications, but they could have gone wrong and they didn't. So to me, it's at least something.
Yeah, those are, it seems, hints. But again, they are just at this threshold where you're at the string size scale for the black hole. And to me, it looks like one of the messages of trying to make black hole evolution unitary is some modification to how we usually think about locality at long distance scales. And then you can ask, how does string theory have that modification?
Yeah.
And you can say, well, strings are extended objects and they get excited when you scatter them at high energies. But if you look at that very carefully, it's not clear that that really is the kind of non-locality and is big enough to solve the problem. So so in a sense, string theory appears to still be maybe too local, at least as we understand it. And so, at least that's kind of where I end up, having looked at some of these things carefully. And so it's not clear for that reason, how at least in our usual way of looking at it, string theory resolves the problem, especially for big black holes.
But
anyway, there are hints, I agree, there are hints in various places, but
what I'm saying
figure out
is,
what to make of those.
Right, but if you include, what I'm trying to say is that if you couple these results with a bunch of other things that you mentioned, that of which we also have some explicit examples, I think the starting point at the current state of things is just, it's a non-zero amount of hints. That's what I'm saying. It's a strictly positive amount. Now, how much you weigh?
It's non-zero, but I don't know how to put a measurement.
Sure, that's fine. All I wanted to say is that we're not just completely in the dark. Of course, we're mostly in the dark, but
maybe
it's better than nothing.
so it would be interesting.
Sorry, no. You go first.
What would be interesting is to quantify, try to find a number for the amount of non-locality needed. And I think there's a paper of yours where you tried it. And then to check different proposals in quantum gravity, whether they can actually reach this amount of non-locality. And I guess the naive picture with string theory is that if you're at high energies, that's the beauty, I think, is this IR, UV, whatever, is that the higher the energy, the longer the string gets. Which I don't say that's enough, but this is, I think, where people sort of got excited a bit that it could provide the necessary non-locality. But again, I trust you if you're saying there's maybe some parametric mismatch.
Yeah, let me, well, I can say a few more words about that, but I really want to broaden the audience. So let me just quickly say a few words about that. So you can ask whether string extendedness and the fact that strings get longer when you excite them at high energies, whether that can do the job. Okay, so, and in fact, there was a paper I wrote with Maharana and Gross. Actually got David to agree to it. Examining at least one aspect of that, and that is, let's scatter two strings gravitationally and try to understand this string excitation effect. And so you have a highly boosted string, like a highly boosted particle, of course, is essentially an Eichelberg-Sexel on its solution. And let's just ask if we have a string coming in and scattering off of an Eichelberg-Sexel solution, what happens? And what happens is it does get excited. It starts to spread out because of what I call tidal excitation. It's connected to what ACV called diffractive excitation, but it's a tidal effect. So it gets a kick and starts to spread out. But then if you ask in the context of a high energy collision that is going to make a black hole, whether that's an important effect. Well, the two strings come in and then they meet each other's Eichelberg-Sexel waves and they get a kick and they start to spread out. But by the time that happens, they're inside a horizon. Okay, so that's what I mean by saying that it's not clear that there's, well, or strings are almost too local, right? They're behaving like, composite objects that are inside of a horizon that are, okay, they're getting blown apart from each other's gravitational field, but that happens once they're inside a horizon, and it's not clear that saves the day. So anyway, that's a quick version of the, at least part of this story. Okay, let's broaden to the audience. Well, one more from the panel, and then,
Yes.
then we'll go to the other.
I mentioned the example of Yam's theory also as an encouragement to all of us, because we have our own theories of quantum gravity, okay? And sometimes it may take long for a theory to be appreciated. It happened in this theory, but it happened because data forced humans to go that direction. I stress it. So the challenge you extended has to be taken seriously, because either you have data, or no matter how beautiful your theory will be, it could take centuries. You cannot hope in consensus to go there, because consensus follows social dynamics laws that I know a lot about, by the way, but they are not governed by rationality. Right? You should worry about the contrary. So when I produced this theory that I presented of universal particles without the predictions, going around giving talks, somebody at some point asked me, okay, now we have this theory, so what? This came as a shock, because I asked myself, oh my God, am I turning into string theories? And so I studied technology because I knew literally nothing about it, and I was lucky that the prediction came out that tensor to scalar. Actually, you can compute everything. And I hope a lot of things will be measured in 10 years, because they promise beyond the tensor to scalar ratio, the tensor tilt, you can compute it with an accuracy of 1 part in a million. But that's it. That's the challenge. So if you have your preferred theory that you want to propose, please push it in this, because this is the only way that you can hope can make a difference. I don't think that 1/4 in front of A is pressing for me, because, putting things in perspective, a black hole takes 10 to the 7 T not 17, 10 to 17 years to evaporate. So we do not know if they do evaporate. It's just, I don't think it is present, but the challenge is the serious challenge. Because I don't know what Yammer's theory would have been remained if it was not useful
Yeah, we
because
all
data. I don't
very
know.
much would like to have data.
Yeah.
Okay, so let's go to the audience. So,
Yeah, so three hopefully brief comments on the different things that have been said. So one, Thomas, you were sort of looking with some surprise at this existing religious belief that from a fundamental theory you will be able to compute the parameters and of the standard model, for example, as a derivation, as a prediction. And I do agree with you with the fact that I also would expect any theory of quantum gravity to have to be rich enough in the type of Vecchia, or maybe containing also not free parameters and so on, to be not predictive in that sense without observation fixing stuff. But that religious belief is exactly how the string theories were presenting, to me at least, the theory 20 years ago. We have a final theory which has no parameters. All the rest is going to be the result of some possibly very complex calculation. We're going to derive the standard model with all the parameters and so on, explain the true string theory. And I found that totally unreasonable at the time. So, I mean, this religious belief is the reaction was like, string theory didn't deliver on that type of promise of string theory itself, and not because somehow we all expect quantum gravity to do that. Related to this, commenting on something that Ivano said, I am personally suspicious of the idea that there is a unique completion of anything we see in the IR, and that complications come also only when you go from the unique theory down there to the IR. This can sound bad, but in fact, I look at it the positive way. I mean, I see the situation a bit like in condensed matter, where we are in some approximation that is valid in the IR after post-graining and so on. And there is universality also going this way. There may be many fundamental microscopic models that, although differing in a number of details, when you take the appropriate post-graining approximation, or you go to low energy or long wavelengths, more or less coincide in some universal feature. And in fact, that would be I am very interested in finding what is shared by many different quantum gravity approaches. Because if we identify those are going to be robust predictions, the universal features. Then once we check that, then we know what is the universality class that works. Then we can start checking what are the details that differ and whether they are also predictive. But I will not expect, I will not necessarily push or require even uniqueness at the fundamental level. And this is one more reason why at the more sociological level, it's very important to just check what different approaches do to see if there are common elements, if things can be, somehow we agree on some prediction or some general formal feature and so on. And I think the third comment I forgot. Stick to two.
responses to that.
Right.
Either from, let's start with, why don't you?
Yeah, maybe because I'm not suspicious of being a great string theory lover. I think I would just not, challenge a theory like string theory or any other by comments and claims that have been made 20 years ago. Because those people are other people than those who are running the show at the moment. And we cannot hold this against. And this is a general comment.
Not commenting again. No, I agree with him. I'm just saying the origin of this backlash is a bit.
We all know that.
We all agree on that.
Some of the initial optimism was not realized in the field.
It's a very nice way of phrasing it.
So,
No,
But it's irrelevant for the young people.
No, I think that accountability requires to keep everything in perspective and take account of everything. I'm sorry, I do not think that you have to forget. I don't know.
But the price has been paid.
History cannot be
No, no, but it's not.
I never understand that comment.
I'm not interested.
Totally.
Why should I find
Why should
fault?
you? Argue?
No, we should learn from history.
Oh, yeah, that's a
You
different
should
thing.
learn from history.
He made a very clear statement about, what the status is. And there was no claim about deriving anything from, the fundamental theories. So
No, there was
Okay, Ivano, please.
Right.
Yeah.
So sociological issues aside, so I actually agree with what you said on that part, and I'm not sure that's what I meant. Maybe there was some misunderstanding of what I meant in that slide about the uniqueness thing or simplicity. I just meant that in this particular sector, this particular UV completion, it seems to be the case that at least certain high energy effects are independent of the particular vacuum or low energy details. That's all I meant.
Okay.
Just to clarify.
Yeah.
So let me take you up on something else you said, which I know it's become popular among string theorists.
You're talking to me or to?
Yeah, to you. And others to say that you don't expect the cosmological constant to be constant, right? So this seems to become a rather strong expectation. And it's not totally clear. I've been to several talks on it, and I'm not really sure what the basis of the claim is. So it's never really put as well, some people even put it as a rather firm prediction, which is great, because then it can be ruled out. But most people don't. Now, when you make some statement like that and don't tie it to a firm prediction,
Neil, can you be more precise? Are you talking about the metastability or the recent claims about runaway?
De Sitter is no. The claim is that De Sitter is somehow impossible in
Metastable De Sitter.
Or
De Sitter, full stop.
that doesn't mean much.
Just to say, a
The
universe.
isometries, are they perturbatively broken or they're broken at some time scale? These are two different, like what Wafa or some strong claims made was more about that there's no realization of the Sitter isometries. There's only near the Sitter isometries, something like a quintessence scenario.
Mhm.
But that claim has quickly been sort of retracted. It's a claim about perturbative regimes, which it's unclear whether our universe is in such a perturbative regime. So the more correct claim would be the firm prediction from string theory that if there's a De Sitter vacuum, it's at best metastable, and you don't expect the lifetime to be much more than it is today. That would be, I would say,
metastable with
it's at best metastable. If there is one, it's at best metastable.
on a lifetime of the present
These are sort of
age of the universe.
Yeah, something like that.
Wow, so we're about to end in a crunch.
It doesn't look good.
It could happen in about
That's a very
100 lifetimes of
Yeah,
100 double times.
so that's a very unfortunate prediction, because
if you see a
confirming
ball
it
coming
will
at some
kill
point,
us.
you would say Kumran was right.
Well,
that
I doubt
you will
we're
only confirm your theory by destroying
by dying.
everything.
that's
Okay.
not what
Yeah.
we're saying.
So yeah, I mean, the basis for this seems to be a belief in an S matrix,
So that's one possible way to go about it.
which
It's not the only
so
possible way.
I must say that from the point of view of cosmology, I see absolutely no need for the universe to be described by an S matrix. So if your theory only works with an S matrix, it has probably got nothing to do with cosmology.
No, but that's not the point.
No, it's a valid point. Actually, this is a debate even in the community, like Tom Banks has been saying. If a theory is built on an S matrix, if the theory is self-consistent, it cannot spit out a space-time that does not allow an S matrix.
Mhm.
I'm not saying how serious one should take such an argument, but there is this kind of reasoning which one can have. I mean, I don't say I agree, but
Right. But of course, one can turn the story around and reason from the bottom up on what kind of well-defined theory of quantum gravity could have no asymptotic boundaries or things like that. I don't really want to go into that right now, but I'm saying this is one line of reasoning, but it's not the only one. That's not the main beef with it.
Okay, so I'm just unhappy about this because people are sort of making predictions, but not making predictions.
Well, one sharp thing
And
that
really, it's just a sort of expression of prejudice, and I think science should be a little bit more than that. It's not a question of sociology. The whole appeal of science is that you make precise hypotheses and then you test them, and if you fail, you learn. And what kind of worries me about string theory is a tendency not to learn. Because, you know, the number of dimensions was wrong. There's
I'm sorry.
That's not true.
The number of
Well,
dimensions is not fixed.
You would have
Number
been
of
very
dimensions.
happy if string theory had only worked in 4 dimensions. People would have been thrilled. So,
Sure, but-
so no, in a naive sense, So I think string theory has become very used to looking on the bright side, whereas actually in science it's often better to retreat. You know, when your expectations are not realized, to say, well, maybe I was going down the wrong road. A more relevant example today is with inflation. Okay, so string theory, for some reason I've never understood, really allied itself to inflation as an approach to describing the cosmos. Okay, many string theorists tried to make string theory compatible with inflation. I mean, fine thing to do, but people who've been working in cosmology knew very well this is a phenomenological model. It's very dirty. It's got all kinds of parameters. There are assumptions about the initial conditions. There are all kinds. Why did string theory, which was attempting to be this very pure, rigorous theory, ally itself with this grungy model? It did.
I am aware that people, I am aware that many people did that.
Right.
But
And
I cannot answer for them.
No,
No, but Neil is absolutely correct.
Yeah.
But the question is, it's related to the comment of Jan. Should we now talk about indeed a strange dynamics which happened quite some time ago? And concerning your first point, actually, I think you're also right. So the good news I would say about the swampland paradigm is to say, okay, I take a step back.
Yes.
Including the early universe. Some people are
Yes.
saying, let's throw away inflation, let's just start all over again.
Yes.
But you're also right saying that people sometimes want to be positive, overly positive, but they actually say, so in the swampland community, we have the statement that the more impactful a conjecture is, the less evidence we have for it, and that means you're kind of optimistic. And amongst ourselves, we know that when somebody's giving this talk, this isn't overly optimistic, but why not? And this indeed, yeah, sometimes I also wonder, should one do this? Because it can backtrack very badly.
That's right.
So I think you're right.
So, I mean, the solution of all this, I believe, is to promote diversity.
This is actually something I completely agree with. Like,
Which is what this workshop is doing. So
What does that mean?
it
Because
means
these are words.
these are only words.
Because I see funding goes
This is right.
always the same direction.
That's correct.
And talking about the 20-year stuff,
That's correct.
there is a continuity
That's correct.
that favors people who are already established in some places. So accountability, where is it? Let's talk about not string theory. Let's talk about supersymmetry. Supersymmetry. How much did it cost?
Right.
Well, let's not go
Let's talk
too
about
much into the
No, that's funding. Let's talk about string theory now. How much did it cost?
anyway.
A panel about string theory, right? So can we compute how much did it cost? This is not a difficult calculation.
It's billions.
I'll let you privately.
My
do that
applications are
calculation.
still hard.
I think you have been waiting to say.
Trying to be
ask a
not
question.
sociological,
Sure.
something related to what you mentioned, Neil.
Yes.
Well, I just want to say to all the parents. So, 10 years ago, when I was master student, my ambition was to do string theory.
Mm.
Then I got a PhD fellowship on string cosmology. I thought, okay, I don't know cosmology, there is string. Let me go and do it. And when I was working on it in the initial years, and I realized what string theory community, large part are doing, basically build a toy model that fits the data, then embed in or create some version of string theory and claim that this model, this toy model comes from string theory. And the whole archive was full of all these papers.
Yeah.
And this is the problem that has to be fixed first. And it's a very serious problem. As you mentioned, the predictions, derived predictions from foundational principles. And no, this is not what people are doing. People are building toy models. It works. Okay, some kind of potential gives n intensity to scalar ratio. Okay, now embed in some version of string theory.
Yeah.
And create a new version. If it doesn't exist, create a new version.
Okay, next.
They wanted
Can I
to,
ask
I think.
Sorry.
They wanted to say something.
Oh, okay, sorry, just.
Sorry, boy, I don't want to take away your question. A very quick response.
You're next.
Yeah, and so the thing is, our field matured. So were many people who got annoyed with, how would you say it, re-inverse engineering effective field theories like inflation, and then trying to find a compactification that does it. I invite you to go to the current string phenomenology conference. There are a few people who still do it, and it's not very fancy. The majority stopped doing this. We are now interested in patterns, exactly for the reason that you say. So I think, honestly, this was not good, but we also stopped doing this.
Okay, that's good.
Yeah.
Self-correction. Okay, yes.
Yeah, can I ask in this context about the statement about not the sitter? Is it possible to say briefly what that is based on?
So you're the sitter.
Or is it just you know, a meta observation about what models we have been able to construct?
No, there's more than that.
There's also this generic observation that, if you have a minimum, there's always expected to be sort of a
Yes.
runaway region in the potential
Yes.
where things decompactify and go down to zero energy.
Yeah, this is
I
the
don't know this.
Dine-Seeberg observation. Yes.
Yeah, it goes
Yeah,
backwards,
that's one.
way back to Dunn.
So there's the general story about the meta observation that you mentioned. Then there's the Dine-Seeberg observation about the fact that a theory with no parameters that has this property of asymptotically vanishing potentials sort of naturally has this order one strongly coupled regime in which you would expect any de Sitter like configuration to live in. And then there are actual, no-go theorems in certain circumstances. For example, the one in 2015, I believe, by Seti and collaborators.
But there are many more.
Many more, of course. There's the Maldacena-Nunez one, actually an extension to non-supersymmetric settings that I worked on, that I proved a few years ago. But I am especially impressed with the one of Seti and collaborators because it works at weak coupling, but potentially any curvature, right? So this is why what I said in my slide was that perturbative de Sitter I would exclude for these reasons. And then the eternal de Sitter has to do with the question of, what are well-defined observables and what survives black hole formations. That's more of a conceptual thing, coupled with the observation that anything that's not protected usually decays without any mechanism. But yeah.
But maybe just to summarize this, so given I think what I was trying to ask is that it's the old Dine-Seeberg, it's no-go theorems from all orders at the worldsheet, but I think that's what he wanted to know, like the recent hype came from an extension of the Dine-Seeberg argument where you also use entropy considerations. And so using those entropy considerations, you sort of get at a firmer statement than Dine-Seeberg. And I think that those considerations also could work beyond string theory. And that's where like the highly cited papers come from. They use some kind of an entropy counting, and then you realize that in a perturbative regime, there should not be a de Sitter state.
Yeah.
But it's heavily caveated. I take a much more naive point of view. We have observations which seem to be really compatible with constant. This was a model proposed by Einstein in 1917. It's a model with a pretty good pedigree. Do you really believe it must be wrong?
No, we say it's not reachable in a parametric perturbative regime. Neil, these are other
that's
so the question is whether the universe is in that regime.
Okay, if I want to know what is the universe, I'm not interested in your perturbative regimes. I want to know what's there in reality.
Yeah.
And that model with the lambda, has an excellent pedigree.
Yeah.
And I'm quite happy to say, well, forget what string theory predicts. That model looks pretty good.
So I sympathize with this point of view. And then my follow-up would be, that's great. Let's start there. Let's try to build a consistent theory which contains an effective field theory like this.
Yes.
And this is, I would love to see
it. And if we need to go beyond string theory, let's do so.
Absolutely. The question is there such a construction?
No,
I would love to see it, and I'm very happy.
I mean, I believe the starting point of that is trying to do something in 4D.
Sure.
And not worry about extra dimensions, because a lot of these complications come about from decompactification. If you don't have the extra dimensions, you're not going to have those problems.
This is.
Okay, Renata has been waiting.
Yes, thank you. Yeah, some questions and comments. So, okay, we've been talking about, so thanks for this nice list with only the one green tick. Yeah, so we've also talked about things, fading in and out of what people think primarily of as string theory and the most important feature. So something that seems to be, going to the background is that of, does this theory exist in non-perturbatively? It hasn't featured anywhere, and one doesn't hear people talk very much about this. But even I would say, Stephen, your first take, having kind of resolved non-renormalizability is somewhat okay. Look, we found that new theory, and of course, it has all kind of low energy implications. But let's imagine this. If this doesn't exist, or we're just unable to show that it exists in any meaningful sense of the word. Of course, that is not so easy to define what that actually means, but non-perturbatively. So what then? Okay, that definitely relates to the question of uniqueness. So first, uniqueness of the theory, which of course was, I would say, phrasing it in a positive way, was one of the grand promises of string theory as the unique theory that unifies everything. So, and then on top of that, uniqueness of the ground state. So Ivano, well, you were somewhat unkindly were referring to religious beliefs. Of course, we should make that.
That was my word.
Yeah. No, that was you. Yeah. Why should there be a unique ground state?
Yeah.
Well, I don't think it's a religious belief, but I would say if nature is kind to us, there are not zillions of consistent quantum gravity theories which could take the form of non-perturbative string theories, but hopefully just some very few free parameters, which we can then determine by experiment, whichever way. So, and then coming to a point that I think Ivano did make, saying this is kind of, what was it again? I'm very sorry. It's inevitable because Akani Hamed says, if I couple the standard model, I will get a huge landscape. Well, there are other, and again, imagine string theory doesn't describe maybe nature in some very deep sense. There are other possibilities that are thinkable. And I'm just saying, for instance, what we are seeing when we are putting gravitational relatives, we're seeing that coupling matter doesn't have much of an effect on those Planckian scales. So at least it's a logical possibility that what dominates, really in the far, far ultraviolet are not these matter degrees. Of course, it's very developing, but at least it's a logical possibility that, there might still be relatively, a unique vacuum or ground state of the theory.
But the standard model claim was not about string theory, it was about the standard model, which we all agree is the correct theory.
Yeah, but it was an argument. It was an argument against the existence of a unique field, including gravity.
Yeah, because we know now that the ground state of the standard model is not unique. So
No, we don't know that. We don't know that. It's only not unique if you forget about boundary conditions.
Indeed,
And you forget about cosmology.
That's the point.
The vacua Akani Hamed were describing are not consistent cosmologies. They are not relevant.
Maybe someone should remind the audience about the vacua that Akani Hamed was. So you want to give a quick?
Very quick. It's really not so complicated. You take the spatial topology of our universe to be different from what we maybe naively think what it is. We actually don't know what it is. So let's say that the spatial dimensions are circles, to just take one example. Then you actually find that there are extremely many ways to stabilize those circles in metastable states, where these circles are microscopically small, and they're stabilized, for instance, by Casimir energies. Okay, so this is a calculation purely in effective field theory that cannot be.
So it has nothing to do with ultraviolet degrees of freedom.
Exactly.
It doesn't understanding. I thought you were arguing against the unique ground state. The mother of all ground states.
No, I was saying that the fundamental theory must contain a standard model, and the standard model already has an extremely large landscape once you include gravity, based on effective field theory calculations. So we know it has to be correct.
Okay, but it could become some completely different theory at much higher energies.
No. So I think where it seems we all agree is that what you expect of fundamental interactions, that they tend to be almost unique randomness. Right? We're just saying there's a difference between interactions at a very small scale versus how the IR theory looks like. That's all. We see it in condensed matter. We see it actually in QCD.
But something is underlying what you're saying, was that you're implying that whatever fundamental theory there is will not explain why our dimensions of space are not curled up in circles. You seem to be saying that. We have to live with the multiverse, whatever the fundamental theory is. And I think that there's no grounds for saying that, because there are boundary conditions which have to be used. There are entropic arguments, all kinds of arguments which could influence the choice of three-dimensional, the topology of three dimensions. And it's quite reasonable to hope that some sort of physical arguments will tell us why our three dimensions are extended.
Is this a difference between vacuum selection?
Yeah.
Or sure. So there could be, you can have a theory with a huge landscape.
Yeah.
It can still be that
some
dynamical mechanisms make you go to one, for instance, Bronnenberger-Waffa, which is an extremely beautiful argument, seems to say that despite string theory having a crazy landscape, simple early universe dynamics seems to make 6 dimensions remain small and 3 tend to always unfold, despite having many more other vacua.
It doesn't really work, but anyway.
Sure, but it is right as an example. As a whole. Yeah.
Right. So I just wanted to say, first of all, everything that Thomas said about the standard model is also true for pure gravity, because the mechanism really doesn't really depend much on the matter content indeed. And as for what Niels said, indeed, the asymptotic super-selected conditions are an external input. So it could be that after we input sufficiently many of this data, the number of leftover vacua may be, small or feasible. I would say at the present time, we just don't know. So that was it. And as far as for the first question by
the existence of a
indeed. So I did.
Where is that?
Right. So I did mention something about it in the slides. So I think the answer is that we don't know if there is such completion, but we do have hints of it. We accumulated some evidence toward this, unique structure related by, dualities in different limits and various non-perturbative effects that you can track from one to the other, or some formulations like the FSS matrix models, KKT matrix models, DBV matrix theory, ADS-CFT, that cover different superselection sectors non-perturbatively, and in some cases can be reduced to other sectors via certain limits. So it is a patchwork. I would say it's currently an incomplete patchwork, but non-vanishing amount of information we have about this.
But no overlap with reality either.
We're working on it.
Right, fair enough.
But that wasn't the question though.
No, true.
So and then what's the end game? So it could be that there is no actual complete theory. Of course, we don't know that. The evidence points to the idea that there is one. It could be that there is one and we will never get there. The optimistic scenarios are that there is one, we will get there. And then there are two options, right? Either there is a single formulation that covers the whole thing, which is something that actually sort of people hope for quantum field theory as well, between the algebraic and functorial and other kinds of formulations. Or it could be, and perhaps it is most plausible of the optimistic scenarios, that there will be a completion of the patchwork while remaining a patchwork, similarly to how coordinate charts on a non-trivial manifold are manifold, not just one. So these are the scenarios I envision, and this is to me a sort of fair representation of the state of things.
Well, I guess in the old days people would have said, well, here is a consistent string field theory, for example.
Right.
So that's.
Can I maybe?
Yes, you can.
Right. So again, to my incomplete understanding, and please, if anybody.
So I tell you because this is much more concrete than patching this and that, and those relations, they're all hints of something that, of course, one wishes to believe in, but it's much better to say, look, here is a criterion, and if that works, that is really incontrovertible evidence for the existence of this non-productive structure.
Right. So I would say that the current, information we have is already some evidence. It's not like about wishful thinking. It's about there is some evidence there. It's we're just not ignoring it. As for string theory, I would say it's part of this incomplete puzzle. As insofar as initially was thought to be maybe a way to a single and all-encompassing formulation, it doesn't do that, and I think we understand why it doesn't do that. At the level of purely open strings, there is a sort of way to make sense of open string theory, right? This was done a long time ago. But I think the reason why closed or open-closed string field theory cannot be the complete story, and perhaps it's a rewriting of string perturbation theory with extra spice, in some sense, that allows certain additional insights, mainly by Ashok and collaborators. The reason is that fundamentally, I think this framework is teaching us that there is no analog of the bare action that there is in field theory. So what string field theory would have aimed to get to is like the analog of a field theoretic bare action that gives you the whole story in principle. And because we understand, ideas relating to holography and similar concepts, that at least in this framework there is no such thing. To me, it's not surprising that string field theory did not get there. Actually, it's perfectly compatible with all these things. And therefore, I regard it as one of these pieces, together with matrix models, with the ESCFT, string perturbation theory, and all the other things.
I think there were a couple more questions. Did you have one still?
Yeah. So we're discussing this morning that there are people who focus on S matrix and other people who think that the goal of quantum gravity should be first to explain why there is why we live in an extended four-dimensional manifold. So my understanding is that string theory has little or nothing to say about this second question, but I would like to
could reply, but so I mean, my comments on this are more on the conceptual side, nothing extremely concrete. I mean, of course, on one hand, at least string perturbation theory seems to tell us that the only well-defined observables, at least in that regime, are of that type, right? Asymptotic observable. But I often ask myself, like, why would it be the only option independently of string theory, right? Which I think is one way to rephrase the question.
No, but wasn't the question about why four dimensions?
In order to talk about a scattering matrix, you first need to be on a four-dimensional manifold, in particular, asymptotically flat region. But forget that detail. You need to start with a continuum manifold.
I actually don't agree with that.
No, does string theory not start by the assumption that there is some continuum manifold dimension?
No, I would say that what you need to talk about an S matrix are asymptotic boundaries. Now, what happens?
Boundaries of what?
No, it seems there seems to be a more abstract way to talk about the structure through holography, in a broad sense, and in the sense, like for example, we have reasonably concrete, like in some cases even exact calculations in certain special cases, like tensionless strings, for example, where essentially we can describe the entire calculation of, say, a scattering amplitude or a boundary correlator in the case of ADS, purely in terms of boundary data, in a way that makes it manifest that the interior is emergent in some sense. And so, like, there's a sum over topologies, for example, of the internal part. And in some regimes, the internal part is not even a manifold. It can be something more abstract, like a conformal field theory that describes it indirectly. So my point is that these indications, at least in this framework, point to the idea that you can define something like an S matrix, fixing the boundary data, but in a generalized sense. Like we call it boundary, but it's not a boundary of something. Okay, it's just the structure that hosts the states and observables.
but at least the boundary itself is a manifold to begin with.
Would say so, yeah.
But was the question more clear?
That's very generous.
Was the question, were you maybe more interested to understand whether the number of visible dimensions can come out as a prediction or not?
No.
Or that was not.
The question is,
In a sense, yes.
Because there's something to say about that, but this is an unfinished story. So well, I think Neil actually knows this one better, but there's an old scenario by Brandenberger and Vecchia where you look at a very small universe. You are say, I'm democratic, and democratic means that I treat everybody the same. So let's say that all spatial dimensions are complex. And then you look at the thermodynamics of a gas of strings, and then it turns out that it's energetically favorable for the universe to decompactify 3 spatial dimensions, and the rest will remain sort of small. Now, we can discuss whether we think that calculation is correct, but there's sort of
we can.
Okay.
We can.
Now, in more modern times, what I find compelling, and I don't think you can find this in papers, is the following. So one of the games of string phenomenology is to compactify 3 dimensions and make sure they're stably fixed, meaning that the fluctuations associated with these dimensions are very high energy vibrations. Otherwise, we would observe them.
But Thomas, I think you're not answering his question. His question's more basic. I mean, even to discuss a torus, a 9-dimensional torus, you need a space-time. And the question is whether string theory explains the space-time.
Well,
and I think the clear answer is no. String theory assumes strings propagating in a background.
Well, no, I think it's kind of, this is why I like string theory. So I think space-time in some sense can be completely generalized. So what you want from the CFT point of view is that you want to cancel the conformal anomaly. And what I think is extremely beautiful is that you can cancel that anomaly by maybe saying, okay, I'm going to do 4 normal spatial directions and then 6 things that come from a CFT, like whatever the icing model or something. So
they're more wild.
Yeah, and then you can do calculations for physical observables. There's no way you will be able to interpret your background as a space-time manifold. It is not. Yet you can just compute observables in physics, despite the full thing to not be a space-time.
Yeah, but you have made that choice. I mean, the one who gave you that specific 10-dimensional object, from some dynamics.
Yeah, indeed, because this is a perturbative description in which the background has to be chosen, and this is not surprising at all. But in certain cases where a non-perturbative description is available, like in ADS-CFT or with certain matrix models, space-time is not actually there, and it does emerge in a more meaningful sense, I would say. Like in the IKKT matrix model, for example, where there is no space-time at all. And one can do like Monte Carlo simulations, for example, to see if some macroscopic dimensions show up.
Yeah, but sorry, Ivano, there's really very little coming out that you would identify with a manifold, certain aspects.
Yeah, I'm saying that there are
it's
ways.
Very, very difficult to make.
Yeah. Like I think
as a general rule.
I mean,
including in IKKT matrix models, even dimension. Of course, people have picked it up recently.
But like the Japanese, the group that has been working on it,
I know
that almost nobody double-checked, or maybe nobody double-checked these heavy computations. But if you look at the abstracts of their papers,
they're very ambitious.
Yeah, but they do say that their simulations on a computer do give 3 growing spatial dimensions.
Yeah.
Again,
I mean, if you look at the details, you will understand that a lot of that is, a lot of flowering language. Okay, let me not say more about the quality of the paper, but it's very difficult. But can I make another? I wanted to connect to a point of Damiano's, that of course, intrinsic difficulty in all, and it's common to all the quantum gravity, is this lack of tests of experiments we could devise to test the theory. And so unfortunately we can just go without punishment, we can go off on tangents and move in epicycles, and that's what I really dislike about the subject. Okay. But I still think it's they're fascinating questions we are asking, and I strongly believe that numerical computations, very roughly of the type I've been talking about, or they're making roads into string theory also. People doing kind of landscape simulation studies. I think they can play the role somewhat of a substitute of reality check. So what are we describing here? How do things hold together? And that's also, I think, how people who do, I don't know, point to you, and often one puts just things on the lattice to have a kind of reality check. Is this something real? Is that something that is stable, it exists, and
It's a Gedanken experiment.
Yeah.
Which
It's
is
not more, it's much more than a Gedanken experiment, because that computation has to be well defined to start with to yield anything.
I'm not using that negatively.
No, it's
Gedanken experiments are the best experiments. They're very cheap.
They're very cheap.
And they can be very impactful. So it's not a negative comment.
But you can argue forever, and the computational miracle computation is something you in principle can reproduce, or other people can reproduce, and they may not be happy to reproduce your Gedanken experiment. So many.
We can all agree that we would like to be closer to observable phenomenology with our theories. So we should think about any avenues possible to reach that. Anyway. Okay, anyone else who has not yet spoken who would like to raise a question or make a comment? Sure.
If you need anyone, I can say something.
No, my question is
Okay. No, actually, it's just maybe share a bit my opinion on the. I don't know anything about string theory, but since also history has been mentioned, maybe I can start from some situation maybe that is slightly similar, I would say, although not very similar, exactly similar. If you go back in the 40s, when basically people were trying to understand quantum electrodynamics, of course, even at that time, there were people who were following quantum theory, trying to understand what then became quantum electrodynamics, but there were also the people who were trying to do something else. Okay. And of course, at that time, there's something else was anyway a good path to follow, because you have to try it, right? And there was actually very good people like Max Born, okay, that for instance, in the 1949, he said, okay, listen, I don't know what's going on with the infinities. I want to make sense of a finite energy for the electron. So let's try to make it finite by changing something. And this way to proceed was not quantum field theory in terms of quantum electrodynamics and normalization, but he wanted to try to achieve some finiteness. And to do that, he had to add some new principle to start with. And this new principle was reciprocity. So basically, you take the Hamilton equation, you change x in 1 over, but you change x with p and p with minus x, the Hamilton equation remain the same. So it was basically pursuing this idea that laws of physics have to be invariant under reciprocity transformation. If you think of reciprocity as some kind of very vague relation with T-duality, some people speak about it. So it's some similarity, let's say. But of course, in the 49, so 2 years before, let's say, 2 years before, the lamp shift experiment was already performed. So people knew that if anything you do, you must describe the lamp shift. Okay. So of course, Max Born 2 years later came, whatever he did, but he had to compete with Feynman, with the Schwinger, Tomonaga, Dyson, and so many other people, right? Now, I just know this story about Born, but for sure there were other people trying to do something else. So it was not a problem just of prediction, to predict something new. You have to write something that is consistent with what has been observed already in the past, which is just 2 years before. And of course, this was a failure. And Max Born, instead of saying, no, I still have to change something, would insist on this, I guess he just gave up, most likely, and trying to understand instead what was understood by other people and seems to be actually not a theory of quantum electrodynamics. It's something that works well to describe interaction between electrons and photons. Who cares about final theory, whatever? You have tools, a framework to describe something, it works. You make predictions. Now, today we are hearing about string theory, and the situation seems to be slightly similar, because I don't care if string theory does not have right now maybe some prediction, which is about something that you have to measure and try to verify the theory. No. String theory
has to somehow be consistent with what we already know. So before even doing any prediction, we need to be consistent. Whatever theory we write, we need to try to be consistent with what we already know. And one thing I think that must be really there is the standard model, not just the gauge bosons and some other part. No, I mean standard model with a Higgs mechanism, spontaneous unit break. We need to explain really what we know that has been working very well. We have observed that Higgs, whatever it is, indirectly there is some decay that we have seen, whatever, we have a Higgs. We haven't seen it directly, but we know that there is a Higgs of something that maybe, if we use it, can make sense of whatever we see in the experiments. And it looks like that this in string theory currently cannot be easily explained, from what I understand.
The word easily is important here.
Sorry, I want
because to me that's not science. That's not a scientific.
No, what I'm saying is that can you reproduce the standard model as an energy limit of string theory? That's the question.
The answer is definitely not no. The answer is this actually, by Douglas pointed out, is an NP-hard problem most likely.
Okay.
NP-hard means it's very hard.
Then it's fine. Then if it's an NPR, then I will just discard something else. But since it's a scientific question, we said one must try hard trying to reproduce.
And people do.
Right. Okay. And it's good people do. Now, let's see what is the current situation. We have the standard model, we have our universe, we have a cosmological constant. Whatever it is.
We have dark energy.
Right, huh?
Cosmological dark energy.
Cosmological constant, whatever it is.
You just
Cosmological constant.
dark energy.
If the simplest explanation you can have of the universe, it works. Just by putting a lambda in a field equation.
I agree with that.
What is simple?
That's not necessarily the only way to do
I said it's the simplest thing you do, it works.
Sure.
Okay, fine. You want to do something more complicated, it's fine. You can do that, but that's the simplest thing you have, it works. Now, you say, I have things that work without string theory, but of course I still have to try to understand string theories. I mean, there are many people working on it, why not? But I think if you really go back and try to compare the story that I told, you say, okay, let's see now then quantum field theory, what can give us? Of course, quantum field theory does not has to give like the final theory of everything. I don't even know what does that mean. I just know that even before going to Planck scale, okay, we know that at 10 to the 13 GeV, we see new effects, more or less, which is something happening that will cause some anisotropies in the end in the CMB that we see. Can be inflation or not, whatever it is, but something has to happen. And if you just take the standard principle of quantum field theory, going beyond GR and try to achieve, for instance, renormalizability, you get something extra that was also mentioned by Damiano and John. You get, for instance, an R-squared term with a large coefficient that explains actually something that we call also inflation, okay, which is the Starobinsky model, by the way. Okay. So when people say, no, we don't have even new physics beyond GR that can lead us, no, it's not true. This is for me an example of new physics beyond Einstein GR, which is telling me, at least to me, well, quantum field theory actually has done not so bad, even for gravity, because we are getting something more as compared to what we knew just in standard GR and the effective field theory of GR. And just by looking at this fact, if I were a PhD student and I had to decide, or as a postdoc, I had to decide what to work on, I would say, wait, I mean, I can see that quantity is such a, I mean, something very simple that we have been doing also with other interaction. You do the same for gravity, and you get something actually that goes beyond GR and explain also something new in terms of observations. But it doesn't mean, sorry, I almost done. It doesn't mean that this is quantum gravity prediction. No, it's something more that you are testing that we never get in string theory of this type.
Never, the word never is not
because in string theory, you will have, for instance, this R-square correction and so on, but they are correction in, as an EFP of GR where the coefficients cannot be large.
You can still have inflatons.
Wait.
No.
Wait.
Yes, you can.
Now, now you can say, I want to do something similar in string theory, putting some fields and try to construct it. Fine, it's fine. I'm just saying that you have something very simple that comes from quantum theory. And of course, you can couple things to standard model without worrying about whether I can recover the standard model because it's already there. So you see, if I just want to conclude this way, so I guess if Feynman was here and Max Born was on the other side, most likely history would have evolved in such a way that quantum field theory would be still maybe going forward, and maybe this current situation string theory would have not been like so promising, I would say. Just because, I mean, it's not a matter of prediction. You cannot, at the moment, it doesn't look like that you can really compete in such an easy way with what quantum field theory has achieved so far.
Okay, responses.
Sorry, I'm too.
Please.
I think you just gave a 5 or 10 minute speech.
Sorry, but yeah.
No, that's okay. About that one should work on BSM, Beyond Standard Model.
No, we don't need to work on Beyond Standard
Model. Whatever you said to me.
No, I didn't say that. Wait.
That means that you put the standard model and you look at some effects beyond, which is very good physics.
No, wait. I didn't say that. Who said Beyond Standard Model? I said you take the standard model, you put it to gravity.
Yeah, but when I said the word, and this comes back to the comment of Renata, when we say the words quantum gravity, I think we have something more in mind. Okay, so of course, either you say we have an observational checklist, fine, your observations first, that's good physics, but we're just adding something else to it. And that something else is, I hope at least we can at some point construct where different people can agree, which is, do you get finite graviton scattering amplitudes? Can your theory make time machines, yes or no? What about, do black holes evolve unitary? So it's like you say, and Damiano says, I cannot measure these things, so I do not care. Sorry, that means that you're ignoring the one thing that I was aiming for, which is inner logical consistency. You cannot not ignore it. I mean, you cannot ignore it. It's impossible. So this, yeah, I mean, and so you cannot hold it against a field that is trying to solve these issues, and for which indeed contact with experiment, which usually by decoupling will always be hard, is a more bigger problem. I think you need both are at least equally important, and it's like you go for one side.
I completely agree that there are open questions to be answered. Okay, but the three that you mentioned, okay, could be like with black hole problems, right? These are not perturbatory questions, which of course most likely need an explanation, and maybe quantum theory is not enough. What I'm saying is that even before going to Planck scale, there is something to do. And you must make contact with that. Okay.
And again, people try.
Yeah, people try.
Yes, fine, try, but
Very few people.
Alessia.
No, I mean, I wanted them to finish. Do we have any that's one? Okay. Because, I mean, I think your explanation from a certain point of view makes sense, but there is much more to consider. So in a sense, you say, okay, we can take quadratic gravity, but first of all, quadratic gravity on its own, without any modification, is not unitary, so game over.
That's why.
First of all, no, okay, in the sense that it's not that.
No, it's wrong to say this. I'm sorry, because it's like if you take, it's like if you take fermions and you quantize them as bosons, then you get problems. It's the same, of course.
No, but then it is
It's a different story. I'm sorry, because you can make sense of unitarity. We heard talks this week.
Yes.
Oh yeah, this week that the theory can be made of unitarity. So we should start with that already.
Depends on the criteria.
No, but
perturbed unitarity.
No, but the point is not. It is non-trivial. So one already has to go a little bit beyond modifying things that we know work.
Because if you apply, they don't work, right? You need to do something else. Isn't? I
completely agree. Everyone here is doing something different than what is standard. So the point is, what do you modify in your theory? And it's more complicated. Like I mean, in theories that are based on plain quantum field theory, so say quadratic gravity, asymptotic safety, and observability. It is, of course, one can couple more easily the standard model because it's there, but it's for free.
Sure.
Okay, so it is much more difficult for a theory that goes beyond the quantum field theory framework to go back to and reproduce the standard model. Another question that maybe is unclear to me regarding the way you phrase the question. What do you mean by reproducing the standard model? Is reproducing the matter or gauge content, or also the specific parameters? Because one can go probably also in string theory, one can go very close to a standard model, but
the specific parameters, then it's still an open question.
For me, I think string theory does not need to predict the value of all parameters. I don't know if they want to do that, but for me, if you don't manage, it's fine. But at least you need to tell me that I can get a field, for instance, like a Higgs field, that will give me really the spontaneous breaking of symmetry, will give me like whatever it happens inside the model and so on.
But
That would be fantastic if you get it.
Yeah.
But I'm just saying that if I got Einstein corrected, you don't have that.
Yeah, Mills and Higgs are predictions of string theory, but not the exact value of the couplets.
Yeah, I'm saying to you. We had discussed this last week.
And typically there's other junk.
Yes, but yes.
We discussed this also last week with Ivano, and it doesn't look like that you have this, okay? So.
No, they have this and more.
Well,
They have this in it.
there are various ways of like sometimes as people already mentioned, you have like something that looks like it plus extra junk. Other times you have simpler things with very few ingredients, but maybe the specifics are different. For example, the would-be Higgs is adjoint rather than fundamental, for example. Like but very simple.
It's all their times, that's the problem, I think.
Yeah, nailing it is the problem. Yes.
Right.
Yes, but that is, I would say, also a problem in the guide. I mean, if you couple it with the standard model, what can you compute later that gives you more?
But what if you get more? I'm just saying, you couple it, then you try to get more.
No, but for instance, in the
Hey, there are
standard
some
model,
people
there
raising
is,
their hands.
Oh,
Sorry.
sorry.
And we should probably,
Yeah, sorry.
No, I mean, we can go a little bit the time, but people want to discuss.
Go ahead.
Very short comment. I mean, Neil mentioned about diversity. I'm just picking up something in string theory, very totally diverse, because there are some people predict that from string theory, you can get solutions like fuzz balls, which replace black holes. But not all string theory people agree with. So my question is that, okay, can you derive something look like black hole? And if it is not a black hole, if it is like fuzz ball and no horizon, etc., we can test it. We can rule out whatever you are proposing, or you can confirm or rule out. Let's say.
And I think some people have been
hear about the status of this.
I think some people have been looking at the gravitational waveforms that are produced by fuzzballs, for example. Maybe people like Massimo Bianchi.
Yes.
No, that's not the question. The question is, does all the string theory people who are, I believe they have all common principles, do you get fuzz balls or not?
Yes. So this.
I can give you my opinion.
Yeah.
I don't know if it. Sorry, I mean.
Go ahead.
I can give you my opinion on this story. I don't know if it's the consensus or fact or whatever. Very different things, by the way. So my opinion is that fuzzballs are a minor, like black holes have a lot of microstates. Like big black holes have a lot of microstates. Fuzzballs, as far as I understand the subject, are supposed to describe a minority of these microstates that happen to have a semi-classical description in terms of horizonless geometry. To my understanding, if you actually count them in a suitable way, you get like a subleading fraction of the total entropy, suggesting that the generic black hole microstate is not of this type, but they're supposed to represent some peculiar black hole microstates. That's my understanding of fuzzballs.
Stephen is an expert, so maybe.
Well, not on fuzzballs, but I talked to practitioners some. I think it's fair to say there are a significant number of assumptions that go into the fuzzball sort of paradigm for describing quantum black holes. And I think it's fair to say that they're not universally agreed on. And so it's very much still a question, I think, of whether that's the right way of thinking about quantum black holes. And I think it's a reasonable question because of the number of assumptions that go into that story. That's a short version. Okay.
Also,
yes,
yeah, please. Returning to the previous question about standard model relation and string theory, I would agree with the fact. Well, first of all, standard model is perfectly renormalizable theory, and nothing new is seriously needed until Planck scale. It can simply live until Planck scale as a renormalizable theory, which maybe can get some more content, particle content, which still can be embedded into a normalizable setting. So the problem comes when gravity comes into the game. So I believe that if gravity problem will be somehow resolved, whether it's string theory or field theory, framework, whatever, then there will be not so many troubles with matter, with embedding matter in the system. Well, so of course you need to reproduce the states, but as I understand that in string theory, it's not a huge problem to get the states living. So it seems to me that solving the gravity problem is more kind of tricky, and once it will be somehow solved, then we might have some nice description.
Yes.
I have some question for you. Sure. I don't know. Practically, I'm very ignorant on cosmology, and it would be nice to hear what you think about this pre-Bang cosmology by Gasperini and Veneziano, and also recent work by Brandenburg of alpha prime correction from duality. Is completely unreasonable.
Yes.
On that note.
No, I mean, there are solutions in string theory which head towards strong coupling. And then the hope was that by using duality, you could propagate those solutions through into a weak coupling regime. I think it's still a hope. It's no more than that. I mean, so do we believe there's evidence for a pre-Bang phase? I mean, I must say, yeah, I think the whole picture is sort of very naive philosophically. Our picture was equally naive, saying that, you know, in a sense, can I view the Big Bang as a transition from an incoming state to an outgoing state? So it's worth exploring. But yeah, I don't think there were any particular predictions of the pre-Big Bang cosmology, as apart from it being allied with inflation, in which case it sort of all seems somewhat unnecessary, that you'd have this pre-Big state and it lands you on a potential, and then you get inflation, you forget about the incoming state. So yeah, I think it never really developed into a convincing cosmology. The Vafa string cosmology, which was also related to the Brandenburger recent stuff. They claimed that more recently, I can't remember exactly when, to get the right power spectrum of perturbations. Those claims were heavily disputed. The trouble is the constraints in GR essentially stop you transporting energy and momentum to large scales. And there are very strong constraints. And the feeling was that their assumption violated those constraints. So I don't think that scenario gained much traction. Yeah, so I think the short answer is that attempts to use string theory in cosmology have not yet proved themselves.
Okay, on that note, unless there's anything really pressing, I think we have reached essentially the end of the 2 hours, end of the week. So let's thank our panelists.